Okay, morning class. Let's begin today's lecture. Maybe I'll give everybody 1 more minute to finish writing up the quiz question, okay? Then we will talk about today's topic. So we're gonna venture into a new chapter of the scattering part and start to introduce what's the structure factor and how structure factor comes into play. Okay? So all right, so let's begin. In the last lecture, we finished the lecture talking about all kind of different form factors, from spherical particles to more complex polymer chains. We can also look at disks, etc. And I finished the lecture by mentioning a software that everybody used to look at this property is called SASView, okay? So I will spend a little bit of time at the end of this lecture. As you see, I bring my laptop today, so we're going to do a quick demo. Then I will post a video for a little bit in-depth tutorial in SASView if you're interested to learn a bit more about software. I'll show you what the software can do in a quick sense, how you can model the data and how you can simulate the pattern, okay? So the main topic of today is to go from structure factor to look at non-diluted system. Okay, so what I show here is 2 paragraphs. One figure on the left, we are USM, so it's golden eagle. When you look at the single eagle, that's basically the form factor. What we are looking at is the scattering profile overall. Okay, so you're looking at intensity versus the Q, and the quiz today asks you about how do we measure I and Q. So assuming everybody mastered that, so we know how we can measure I and Q, we can get this curve. This is important because the shape and the intensity of the curve determines the electron density and the shape of your particle. So all these factors will tell you how individually this particular particle comes into play, right? So that's form factor. Then a lot of time we're not just a single identity. We group together, such as this classroom, we would have multiple views. So when 2 particles are fairly close, like those birds in this wires, you will see additional features coming up. Usually show up as a peak, okay? A broad or sharp peak, either way. It will tell you, this particular peak will tell you the information about how those individual particles are linked to each other. So we are more looking at the space in between. So put it a simple way, if you look at this classroom, the form factor measures how each student's height, weight, etc. shape. The structure factor in this case will look at more complex behavior, okay? Let me turn on do not disturb. This particular measures the distance, so how far Nathan sits with Ben and vice versa. This look at this property, dispersion. So how does structure factor comes into play in a theoretical level? So we talked about interaction between single electrons, molecular. So this is an example of disordered liquids, okay? When you have liquids coming up, let me do one more thing. When you have liquids come up, when they are closer enough for each individual particle, the scattered X-ray from this particular particle, from its form factor, will has the ability to interact with the other one. If I only pull this one out, then it's very unlikely it will interact with the other. Okay? So that is an example of disordered liquids. So let's think about water. Water is a great example for highly densely packed molecules, but they lack of long-range order. Pretty much resembled in this. There is still a certain short-range order. What do we mean by short versus long? Short means it's just localized interactions. For example, I can claim the average distance, if it's for closely densely packed systems, gonna be similar to roughly the diameter of a given liquid sphere in this case. If you draw a sphere about this range, it will be within roughly the size scale of that. But when I look at second particle, not the closest neighbor, then the ordering is starting to get more disorder. You can see this distance is no longer closely matched in here. That we call short range order. When you go a little bit further away between the distance, the packing order is lost. It's just very localized. I can see my neighbor, that's it, but I don't see the neighbor's neighbor and so on and so forth. Long range order, we're going to talk about just in a little bit, where you can see much further distance. It can be preserved in many molecules, so on and so forth. That's a characteristic of crystal lattice. So how do we treat this particular structure factor? Not too hard. All the knowledge we learned from simple scattering geometry still applies if you have a particle. This figure looks very familiar, right? So in this case, you're still looking at the scattering from, instead of this is a single electrons, now it's just a collective of electrons. So this could be atoms or a particle. Okay? And if you deal with gold nanoparticle, this just represents a single gold nanoparticle. That's the other one, separated by a distance r. So the beauty of scattering theory is it applies from multiple levels. It applies to single electrons, to atoms, or in this case, for a collect body of particles. So if we look at here, this is almost the exact equation what we showed when we consider the scattering from a single particle. This is a collective particle, okay? We need to sum up what's the form factor for individual particles and exponent of I, Q, R, J. Again, Q is scattering vector, R, J is just the correlation, the distance between one particle to the other, the vector, okay? So, and we know when we do integration of exp IQR, this would give you a sine x divided by x function, or sine QR divided by QR if you replace the x with QR. Okay? So this is the same as form factor descriptor. Exactly the same. But how do we translate it into something tangible and we can see and we can know? Again, I'm going to show a little bit of equation. It's not that hard, and one of the quiz we ask is how does form factor link to scattering intensity? So you need to take a square and take an average, because intensity measures the amplitude. Amplitude square is basically what it collects. So if you have this information, replace F and Q form factor for individual particle, we can reach this equation because intensity is square of F multiplied by another F. What the beauty of that is, if everybody recall in the polymer physics class when we talked about vector, there's self-term. If form factor is multiplied by itself, we call it the self-term. We can pull this part out. It's just the F1 square, F2 square, what this term represents. everything is self-term, and we have cross-term. When j not equals to k, that means fj is not the same as fk. We need to consider a separate term. The reason we want to pull out the self-term versus cross-term is now we can simplify this into this particular equation. nf squared is there basically says you just need to count how many particles. Particle represents by this n number multiplied by form factor square. So if you recall, if we just measure one particle, no neighbors, intensity will equal to f squared q. So this basically is just counting how many particle has contributed there. Okay, so that's represented by nf squared q. And this is the term that's come into the cross term when particle A is interacting with particle B. Okay, cross term or non-self interaction as showing here. So here now we can define a structure factor. This is where a structure factor comes in play. SQ, S stands for structure. Here again form, F stands for form. Structure factor is dependence on scattering vector. Q is a function of Q. And S and Q is basically defined as if we pull out mf squared, this will be equals to 1 plus this integral term as defined by here. Okay? So that's fundamentally how structure factor is defined numerically. And I'll show a few examples how does a structure factor looks like in three representative system. And three representative system we're going to cover today are very dilute system. This is one case. This is a little bit concentrated but without order system. This is second we're going to cover. And we're going to cover a last one is close packed but also order. We're going to review what the structure factor for these, okay? So how do we explain the structure factor to someone who never touched the X-ray? And this is actually a very nice slide. Explains how we should understand in a simple way in terms of form factor and structure factor. So the top equation is basically the same as we described. Scalar intensity will be proportional to a constant, which is defined by scalar length density difference. Size distribution n, which is also important. But more important is last two, form factor squared, as we showed, and structure factor. Okay? So if you use integrate, when A multiplied by B, we call it a special way we can understand is you just need to understand it's a complex form. What you need to learn, form factor is basically individual shape of any particle. Okay? Structure factor is tell you where each particle are located. So the whole picture could be like this. You have particles arranged in this way, but form factor tell you all the information of individual one. Structure factors tell you the lattice order. There's no shape embedded in each point. It just tell you the location. First one is very dilute system. So dilute that your particle is not interacting with the other one. So if we plot GR, you can think about that as relevant to your structure factor. Structure factor is basically a constant value of 1. That means we just measure form factor. Structure factor is a constant. That's the beauty of why, if we want to study the shape of individual particle, you can measure the shape of it in concentrated system, but you really don't need to get all the trouble of measure the form factor and structure factor and then take out structure factor, then leave what left is form factor. Right? You can just dilute them and you can save you a lot of time, because now in dilute system your structure factor is a constant and it's 1. Okay? And
Dr. Yu,
yeah, please.
what is along the x-axis of that graph?
This?
Yeah.
This is arbitrary distance, which is defined as distance divided by radius of this particle. I think it's more obvious here. I think in this, let me explain, this one is a little bit more clear what this value is. 1 defined as the distance from a d divided by the unit distance. So in this case, d gr equals to 1. R means most probability to find a neighboring particle. Okay, so that's just a normalized average distance from the nearest neighbor from this particular particle. In this classroom, there will be the distance to your closest landmate where you sit. Okay, so let's look at a little bit concentrated system. If you recall, this is no longer a flat line. There is an increase. There is a drop to 0 at very, very close. And then there is a sharp increase. Then there's some modulation in your intensity. Modulation means up and down. So in this particular case, then your structure factor or scattered X-ray from this particle and this particle could have the potential to interact. And interact in a either constructive or destructive way. That result in measure intensity differs with a pure single particle as a form factor. Okay? So any question for this part? Particularly, a great example, I found this particular figure is nice. Look at disorder liquids. Disorder liquids basically is just water. You can think about that. Water molecular has a lot of mobility, it will move around. But it's just that there is no long-range order unless it crystallizes. Then it's fixed into the lattice parameter. So for this one, let's take a look at let's draw a circle from the center. Then let's increase the circle radius. So at very low value, we don't have any other particle because the space is solely occupied by myself. Once it starts to hit this distance, it starts to sense another particle, and if you keep going, there is a high probability centered around here, you can find another particle. Then if you keep going on, you likely find another high probability, find the second closest distance. But the more distance you go, because there is lack of high order, you will have chances to see everything go. So this is nearest neighbor of probability, first, second, third. And what this one shows is basically the structure factor people measured for a given liquid. Okay? This is a plotted intense SQ, structure factor with a Q. And using this, 2 pi divided by Q, again, you can measure what is the average nearest distance from 2 neighbor molecular. In the liquids, that means it will be fairly close. GR is called radical distribution function. You can do it in the molecular dynamics simulation. It basically measures the pair distribution. Pair distribution means exactly what I explained. What's the probability to find another atoms at a given distance? So in this classroom, I can claim I find another student within a radius of half meter, 0, find 1, pretty high. That's my first closest neighbor is going to be Michael, Mark, and Nathan. Okay, but as I goes forward, this kind of disorder system will start to lose its order. And when it's far away, S and Q will be attenuated, almost equal to 1. That means I lost any order in there. This is important for anything you want to measure at the highest scattering angle in liquids. Let's say I want to measure my polymer in liquids. At low Q, as I mentioned the other day, in low Q, our ruler is bigger, the measurement scale. So all the water liquid's going to behave like a uniform scattering length density. So there's nothing scatters at low Q region. But as you increase the Q, your ruler or you measure the size scale drops. When it's hit the distance between interparticle distance, it will show a very stronger scattering and broad peak. We call it amorphous scattering. For water, it will be very broad, very large. If you want to study anything within that size scale, you're typically not able to see because the majority of the sample is dissolved in liquid, so your liquid has a much bigger scattering volume. It will overpower any signal. But in small angle region, that's not a concern. Okay?
This applies for taking the Fourier transform of any image, correct? You will always get that amorphous thing.
Only in the appropriate size scale. The answer is yes, but only in the appropriate size scale. You understand? So if you water molecular packs with another one within, let's say, 2 angstrom, you would observe a peak right about 2 pi divided by angstrom. But anything larger than that, you wouldn't see that peak. You wouldn't be able to resolve it. Okay? Any question for this part? Disorder liquids? Quite straightforward. So a very interesting part is the structure factor, as we know, it's equals to 1 plus, it's right on the top. I think I added somewhere. So structure factor is equal to 1 is the self-term, right? Which where that 1 is coming from. And plus number of particles and 4 pi r squared is just the integration in terms of pair correlation function multiplied by sine QR and divided by QR dr. So this is basically a Fourier transform if we take 1 to the other side. So SQ minus 1 will be equals to this particular equation. This is basically tell you SQ minus 1 and GR minus 1 is basically follows Fourier transform. You can do forward Fourier transform to get the structure factor, just to know the electron density or pair correlation function, or you can use pair correlation function to calculate structure factor. They are equal. It's just forward and backward Fourier transform. Okay? Okay, so this is called structure factor for slightly older, short range order liquids. In polymer cases, you can think about maybe the closest thing would be amorphous polymer. If you do scattering in amorphous polymer, you might see this amorphous halo. Amorphous halo is relevant to this short range order due to the Lennard-Jones interactions or packing. Okay, the last case I want to cover today is the concentrated but ordered system. This is more relevant. I think most of you probably heard about XRD technique. X-ray diffraction. It's basically a very specialized case in X-ray scattering in general. Diffraction means there are sharp diffraction spots in the detector. Scattering is just a more general term to describe any scattering phenomenon, okay? So this one, long range order. What do I mean by, I just need to know the lattice unit. Lattice unit, basically lattice distance, lattice angle. I can reproduce the whole pattern. If I tell you, I just have this lattice constant A and this B, and this happens to be the same length. Let's call it diameter D. This D is same as this distance, okay? So if we know a diameter D, if I know this angle, I can reproduce this lattice because I just need to repeat it again in one direction, in the other direction. I can reproduce this pattern. This is true for all kind of crystalline structure, sodium chloride salts or crystalline metals, golds, etc. They could form this highly ordered structure. Okay, so now what makes this interesting is now look at we know the form factor of a spherical structure will look like this, right? That's we have talked about many times. But the structure factor is basically a few sharp peaks. The sharp peak is basically given rise the structure factor or Fourier transform on pair distribution. And we know the pair distribution basically means the distance. Every this given distance, we can find a pair of the structure. This is a one distance. In double the distance, we can find another pair as well. So that means every distance R divided by D, we can find closer to packing. The chances of finding another structure in pair correlation function is high. Double the distance or triple. Okay. And this gives rise to very, very intense scattering peaks. And as I mentioned, scattering intensity is a convoluted product of form factor with structure factor. So if you have a structure factor which shows 0 value in this region, you're gonna take away all the contribution from form factor. You know, anything multiplied by 0 will be equal to 0. So your intensity show up in the detector can be dominated by the structure factor. Show us a sharp peak right at here, right at here. Okay? So in other words, the form factor is no longer can be measured or back calculated. The structure factor dominate in this case. But a lot of time we don't need to know structure factor, form factor, sorry. We don't need to know the form factor, right? For example, we have a polyethylene crystallites. We know what is each individual repeating unit in that. We can probably get a pretty good idea what the form factor is. But in this case, we're more concerned about structure factor. Or in this case, the lattice packing of your crystal. So we can use this pair distribution function to calculate out what is the lattice packing for your structure to measure the distance from here, or in this case, it's hexagonal packed lattice. There's also face centered cubic. There's many other parts. We will cover in the textbook in the chapter 4. It talks all about different lattice and how we can use Miller indices to describe different crystals. So in that case, you will see, if you read the paper, you might see some people talk about 100 peak or 121 peak or 121 complex peak. What are these means? We're gonna go through once we talk about the lattice indexing and understand how we can use that to understand how the packing in the crystalline domain at atomic resolution, okay? But structure factor is not necessarily need to be crystalline structure, right? Crystalline structure is one very useful example of that. We can use the Bragg laws to back calculate based on the 2 pi divided by scattering vector Q. We can get a real space information. That's most predominantly used in many research fields. But if you have ordered structure, you can do diffraction. This happens also at the length scale. Let's say if you use a block of polymer, which our group previously does in my PhD. If you have regular distribution of a certain domain, a minor domain, then those minor domains will show up a very strong scattering peak reminiscence of this structure factor. So I know Kyle is looking at me. He has working on similar problem. In this case, we are not necessarily able to measure the domain shape and domain dimension, but it's the domain spacing from one center of one domain to the other. Okay, and the other part could apply is such as in more larger scale. If you have a photonic crystal, that's also relevant. It's basically bending and diffraction of the visible light within 100 nanometer of these regular lattice. Okay. So any parts on this, on how the structure factor could come into play to tell you the lattice packing if you have long range order? Any question? Okay, great. So there's one. I think this is one last slide I want to cover today. So this is an example of a ubiquitous material for our body. It's water. So there is a nice review work published a couple years back in 2016. This is talking about X-ray and neutron scattering of water. So water is a unique molecule. It is liquid, so that means it's disorder. So you can see how water, represented by oxygen to hydrogen, can form this short-range hydrogen bonding and show this interesting behavior. So if you do MD simulation, you can get a G is pair distribution function. Pair distribution function you can just read as the distance between one molecule to the other. So if you do MD simulation, you can see the pair distribution should show 3 different parameters. Oxygen pair distribution will show a high chance to show up at about roughly 3 angstrom. That means that's the average distance between this oxygen and the other. You can also look at, of course, this vibrates and move around, so that's just the average distribution. It's not infinitely sharp as well, right, as you can see. And you have first neighbor, second neighbor, third neighbor for anything relevant to oxygen. You would also have hydrogen, oxygen, and hydrogen. This is the most closer just because of the hydrogen bonding. And most well defined as well, the sharpness of the peak. As shows pair distribution function. So if I ask, in this classroom, the pair distribution function will be the distance of one desk. You can find another student, okay? So if you do a Fourier transform of this, you get the structure factor. And as we know, structure factor in this case will be dominant. So if you look at this, will represent if you throw a water in your scattering experiment, it will show up a very dominant peak and a shoulder and more shoulders, high orders, in terms of pair distribution function. So this happened to be 2 pi divided by Q. It is about 2, so that's about 3 angstrom. Right about here. Because oxygen, I think that's reason because the contrast is highest scattering length density. Okay? So that's a good example. Show you what is the disorder system will look like. with that, I'm gonna finish particularly the lecture part for today. I saved some time for the SAS view software. So before I move on, switch your computer to that one. Any question for explanation of structure factor for 3 different cases? Okay, great. So now, using the next 10 minutes or so, I'll discuss with everybody and do a quick demonstration of what is SAS view software and how we can use that to model the form factor. You can also model the structure factor, but most commonly, form factor is used. As you see, I already opened the software, so you can download it. It's an open source software, very easy to use, can be installed on Windows or Mac. When you open it up, this basically asks you, let me open it up one more time. So you see, what it looks like. Okay, so since I don't have a real data, I won't show any in the data panel. And this is a fitting panel. As I mentioned, we have a more detailed review if you want to take a look, okay? So in here, where you can actually choose different models. If you look at this particular panel, it tells you what kind of model is available based on different category. So if you want to simulate or model a cylinder, a lamella, a shape independent, whereas Gaussian coil is, or sphere, they're all located. So let's use a sphere where everybody knows. There's also different spheres within. There's a fuzzy sphere, there's a linear pair. So how these interact or impact your modeling is the parameter. Let's use the most simple one. So if you look at it, will give you a few panels. If a sphere, if you want to model it, there's one important parameter is radius. This is not an RG, but this is just a hard radius. What's the size of it? And unit is in angstrom. And the other parameter comes into SLD or scattering length density. One is solvent, one is your sphere. That defines how much contrast you have, okay? And the background is just a constant background. Every single instrument you measure, there always going to be a background that will smear out some of the weak scattering signal. So let's use just a simple one, 50 angstrom. Let me add a little bit more data points, and let's take a look at the Q up to a little bit higher so we can see all the shapes. So if we click calculate, this is going to calculate out the form factor, or in this case, it's more direct. It's just going to calculate the intensity, form factor square, versus scattering vector Q. Of course, this is a perfect case. There's no dispersity in this particle. It has a reasonable good contrast. So that's where from first dip, if everybody recall, we can use either this location to calculate what the diameter of your particle, or we can use the Ganier region, signified by the plateau of your structure to calculate the RG. You can also visualize all kind of other structures within the software. So let's say we want to look at a cylinder. And in simple case, it's just a regular cylinder. In this case, same scale backgrounds will give you, but now you have the freedom to change what is radius and what's the length. A cylinder has a certain length, a certain radius. So let's use the default one to take a look at the property. So this would represent a scattering from an idealized cylinder with a certain diameter and length. So let's increase the length a little bit to show you the software is very useful, helped you to understand what the expected scattering pattern. So if our length is going to be bigger, as you see, this is automatically reflected here. The changes are, this part of the shape now bending, no longer flat and bending upwards. We lost our Ganier region, which is signaled by flattening of our curve. Let's also take a look, what if we increase the radius? Any guess? Let's make it 200. So all the lower, pay attention to this part. This part is relevant to radius. So this part will show quite a dramatic change. As we see, it's shifted upward. So this helps you to visualize any structure or shape you want to model. There's also more complex models, such as barbell, which shows a cylinder with two ends. You can tell it what the end radius are and what the lengths are. You can calculate what the scattering pattern will look like. Okay, so as you can see, this would show quite a different scattering. So you can resolve. You can use this more commonly used as model. You give it a model, you ask it to back calculate what the length, radius, etc. you want to know about a given scattering curve. I'll post a link in the Canvas if you are interested to learn more about software. The software itself also has a very nice menu comes with it. Within that explains over hundreds of different model people already described based on the very generalized intensity versus form factor equation we talked about. So you just need to write a code, and you can use this approach to calculate whatever form factor you want. Okay. This is something optional. If you'd like to know more about it, feel free to read that. But if you're not using it, I would say, at least for me, in my case, I tend to forget about the software if I'm not using it for a couple months. So when you need it, go back to review the video. Okay? Any question more for today's lecture?
So if you get raw scattering data, say from like a synchrotron facility or something like that, can you import it into the software and generally fit it to whatever model you?
Yes, yes. So let me explain a little bit workflow. How do you do this? Let's say I want to measure the shape and size of a new polymer I made, and I want to know how rigid they are. You should start off by understanding what scattering length density of your polymer and your solvents. And you need to actually, in real case, measure a polymer dissolved in solvent scattering. And you should also measure an independent separate sample, just solvent only, no polymer. Although in the pair distribution function, we showed that your solvent majority scatters at a high Q, where it is relevant to the intermolecular spacing. But in low Q, you still have certain backgrounds. So you need to measure that polymer plus solvents, take away all the scattering from solvents. Then you import the data to here. Then you tell it what the model. Let me show you. There's a couple of different models with respect to polymer. In the cylinder, there's actually a model relevant to what we do. Is called flexible cylinder. I want to show everybody. Okay, there indeed is a help. This shows you what the model here looks like and what the model is, explaining all the detail, what each parameter is. Cone lengths are what are it modeling, and it shows you the definition of it, and showed you example, and showed you as well as the equation to describe it. Particularly here. Okay? So if you're interested to learn more about that, it shows every single data for that. Then you just need to ask the software to fit the model to the data you imported. And it will give you the results of the radius, in this case, cone length and contour length for this particular partner. Okay? If no more question, the next class I would like to either we can use that as Q&A time to answer some of the questions you have, because the next chapter will be slightly different. We're going to talk a little bit about short range order for a few unique cases. Water and gas or anything else is basically going to display the same. But there's a couple unique structures as shown in the textbook, going to show a little bit intermediate between the short range order, long range order. That is liquid crystalline polymer. That would show a unique, I had to put the words on, maybe we should call it intermediate range order. There is pneumatic phase and somatic phase, which has the ordering in a given direction but not the other. So it gives out quite unique scattering structure. We will cover that one in the next lecture. Then down the road, we're going to start to talk about all the lattice scattering from all kinds of different crystals. If you're interested in indexing of your crystal, that's a good way to go. Unfortunately, most of the polymer, they don't crystal well. If you want to use indexing ability, it's mostly used in small molecular or in organic material where they create very nice large crystal, almost defect-free. Then you can do diffraction. It will show beautiful diffraction spot. Very much like if you look at this chair, there's beautiful patterns. In polymer, because there's only, the crystal is good, but not that good. You would typically only have a few diffraction spots, 3-4 spots. Instead of a nice small molecule crystal, it will look like night sky. You will see hundreds of diffraction spots, which is very easy to resolve the structure. A very powerful area people has been used in the early days of X-ray is actually to solve the crystal structure for many biological polymers. If you use biopolymers, they have a unique ability to crystallize in a very, very ordered fashion, much better than most of the man-made polymer. So you can do calculation about all these, how these crystals are being made, and use that to get the crystalline structure of certain material. They are widely used in synchrotron beam line, and they are widely used for developing new drugs or new medicines. Okay, so let's finish it here. Then we're gonna regroup next week. Okay.